Hi, good morning. Last class we have discussed about dual operator. For a bounded linear operator a from x to y, its dual operator a star is defined from y star to x star. Okay, and it is defined as a star phi is equal to actually a star phi is equal to f of x, and this is same as phi of x. Okay, actually a star phi of x, this is equal to phi ax. This is our definition. Okay, now we are moving to some notations. Okay, let x be any normed space, let x be any normed space and x star be its dual. Okay, for f belongs to x star and x belongs to x. Okay, x be any linear space, x star be its dual. Okay, for any f belongs to x star and x belongs to x, here f of x, we have written f of x. We denote this f of x, we are changing the notation f of x as this notation x f, and it is same as our inner product, notation of inner product. Okay, I don't know what we call this notation in this bracket x f. That means when you see this notation in I don't know whether we call this as inner product, xf is equal to actually f of x. This is not inner product. Okay, this is just notation. Okay, now we are moving to this is actually let x be any space and x star be its dual. Okay, now we are moving to general. Okay, linear space, let E be any let E be let E be any linear space. Okay, and capital F be space of all functionals on E. When we call this pair xf, then we call this pair is actually a pairing between uh, E and F. Okay, this notation here. E is the E be any linear space. F is the space of all functionals on E. Then this XF is called pairing between E and F. Pairing between E and F. Clear? This is all these are just notation. Okay, XF is called pairing between E and F. Now we are applying this notation to uh, x and x star. Okay, for E we have x, for F we have x star. Okay, now what about this pair? This pair is actually xf. Okay, now what about dual operator A star? We have dual operator for F belongs to Y star. Okay, or some phi belongs to, notation is phi belongs to Y star. We have A star phi of x is equal to phi of ax. Okay, A star phi of x. Okay, so here phi of ax. Okay, so this notation actually phi of ax. So here f of ax means x f, phi of ax means ax comma phi, and this is equal to, this is a star phi of x. Therefore this is actually x comma A star phi. Okay, and as this is true for every linear function, actually what is this? We are going to write like this. Actually, ax phi is equal to phi. And we have ax, suppose for any f belongs to x y star, for any f belongs to y star, a star x f is equal to f of ax, and this is same as a star f of x, and this is same as x a star f. Okay, so the result says that for any f belongs to f belongs to for any f belongs to x star and x belongs to x, ax f. I don't know whether we call this as inner product. We can't call inner product. This notation, I don't know what we call this notation as. X a star f. Okay. So now we are going to prove one problem. First one, if A belongs to LXY and B belongs to LYZ, then we have to prove that BA star is equal to A star B star. Okay, and it is a map from Z star to X star. Okay, so A is a, what we have to prove? If A is a bounded linear operator from X to Y and B is a bounded linear map from Y to Z, then B A star is a map from is a dual operator from Z star to X star. Okay, so here, okay. So what is actually A? A is a function from X to Y. Okay. B is a function from Y to Z. So clearly BA is a function from X to Z. So what about BA star? BA star is a function from Z star to X star. Clear? Now what about A star? A star, B star. Okay. What about B star? B star is a function from Z star to Y star. A star is a function from Y star to X star. So A star, B star is a function from Z star to X star. Okay. So B A star, clearly both are functions from Z star to X star. Now as A, B are linear, B is also linear map, etc. Okay, bounded linear map, etc. Now we have to prove B A star is equal to this one. Okay, here, but is actually what is B A star? B A star, we have to find B A star. Here, suppose some phi. Phi belongs to Z star. Okay, what is this actually? But how we can evaluate this? What is A star phi? By definition, By definition, A star phi, actually A star phi of x for any x, okay, equal to phi of ax. This is our definition, okay, for linear function f and linear function phi and x belongs to x, okay. Therefore, for any phi belongs to z star and x belongs to z, be a star of phi, okay, actually we have to find of x, and this is equal to a star phi of x is phi of ax, and this is equal to phi of ba of x, okay, and this is equal to phi of b of ax, okay, and this is equal to phi b of ax. What is phi b of ax? Phi of ax is, here phi of ax is a star phi of x. Therefore, phi b of ax is a star phi b of x. Phi b of x. Sorry. Actually, a star phi b of x, okay, and this is equal to a star phi b of x. Now phi b of x is same as a star b star phi of x, and this is equal to a star b star phi of x. Thus for any z belongs to thus for any x belongs to z, we get b a star phi of x is equal to a star b star phi of x, okay. This is true for every x belongs to z. This implies ba star phi is equal to a star b star phi, but this is true for every phi belongs to z star. This implies ba star is equal to a star b star, okay. Now, okay, we have this notation actually. Ax f is equal to x a star f, okay. So in the case of Hilbert spaces, for any a belongs to L h1 to h2, that means bounded linear map from h1 to h2, we denote the adjoint operator. We will discuss adjoint operator later. A belongs to L h2 h1, defined by the relation inner product of ax y is equal to x a star y, for x belongs to h1 and y belongs to h2, okay. In the case of Hilbert space, for any a belongs to h1 and h2 are Hilbert space. A is a bounded linear operator on boundary linear map from H1 to H2. Okay, in this case, we define the operator adjoint of A as inner product of AXY is equal to X inner product of X A star Y. Okay, this is actually the notation is inner product of AXY is equal to, in the case of Hilbert space, this notation is actually inner product. AXY is equal to inner product of X A star Y. Okay, now we are going to solve one problem. Consider next example. Consider K T2 belongs to L2 of I2. We already discussed this function where I is equal to closed interval 0, 1. Okay. Now we are defining, here we define an operator K on L2 of 0, 1 as Kx of t equal to integral 0 to 1 K T tau. Okay, here actually tau t. It is not tau t, it is t2. T2. Okay, K T2 x2 d2. We are defining kx of t equal to integral 0 to 1 k t2 x of t d2. And we have to prove that the operator adjoint operator, it is a Hilbert space adjoint operator k star is given by k star y of t is equal to integral 0 to 1 k tau t conjugate y of tau d2. Okay. This is what we have to prove. The operator kx of t is defined like this, integral 0 to 1 kt2 x2 d2. Okay, and we have to prove operator k star is defined as conjugate x y of tau d2. Okay, so moving to proof. We have defined the by definition kx of t is equal to integral 0 to 1 k t tau x of tau d2. Clear? Now what about inner product of kx y? By definition, inner product on L2, this is actually 1 kx of t y of t conjugate dt. Okay, and this is equal to integral 0 to 1 kx of t is this one, integral 0 to 1 k t2 x of tau d2, and then y of t conjugate dt, and this is equal to integral 0 to 1. Okay, I am taking this this step x of this is with 0 to dt, then d2. Here now I am replacing this as dt d2. So for this I am taking x to outside. Okay, so this is actually x to x of tau integral 0 to 1 k t tau y of t conjugate dt d2. Okay, and this is equal to integral 0 to 1 x of tau integral 0 to 1 kt tau you can write as k t tau conjugate again conjugate. Okay, y of t conjugate dt dt, and this is equal to integral 0 to 1 x of tau and integral 0 to 1 these two y of this term we join these two terms k t tau conjugate y of t then whole conjugate dt. Okay, dt, and which is equal to integral 0 to 1 x of tau integral 0 to 1 k t tau y of t, here we have conjugate dt, this you can write as whole conjugate dt. Okay, and this is equal to integral 0 to 1 some x of tau some y star tau conjugate dt, where y star tau is equal to integral 0 to 1 k t tau, okay, conjugate y of t dt. Okay, so actually what is this one? This is equal to, this is integral 0 to 1, therefore this is actually inner product of x y star. Okay, so what we have now, we have inner thus we get inner product of kx y is equal to x y star. Actually this is by notation, this is equal to x k star y. Okay, and k star y is defined as, here k star y is actually y star. Okay, that means k star y of tau is equal to y star tau is integral 0 to 1 k t tau conjugate you can write. Okay, k t tau conjugate y of t dt. Okay, so here k star y is the, if as H is a Hilbert space, k star y is the adjoint of k. That means y star is the adjoint. Therefore, adjoint operator is integral 0 to 1 k t to y of t dt. Okay. Therefore, here if you replace this notation as some y star t, what about k star y of t is equal to integral 0 to 1. What do we have to write? K, you replace t by tau and tau by t. T conjugate y of tau d tau. This is actually tau from the k t dt t tau. Okay, so I am replacing tau by t. K star y of t equal to integral 0 to 1 k tau t y of tau d tau. Therefore, this is the adjoint operator. So today we have discussed the notation of dual operator for any x belongs to f and f belongs to x star and x belongs to x. We denote f of x as inner product of xf. Okay, I don't know whether we call this as like this. Just for convenience, we call this as inner product xf. But this is not actually inner product because we have defined inner product only in Hilbert spaces. Okay. And another notation is if in the case of dual operator, we can denote this like this. Y is equal to x a star, sorry, inner product of ax f is equal to x a star. Okay. Now also finally we have discussed one problem for finding adjoint. That's all for today's class. Thank you.